Hi, my name is Jen, and this is the third in a series of workshop recordings from MAT 133. If you would like to attend a live workshop, please check the workshop calendar for the schedule. Also, keep in mind you can ask questions in the discussion board in your course or in the online Math Center learning community. Watch the end of the recording for information on finding the learning community. In this recording, we'll be talking about probability. So let's start off with some vocab. Sample space is all possible outcomes of an experiment. An event is a subset of outcomes from the sample space. A simple event is one outcome from the sample space. A compound event is two or more simple events. So let's look at an example. Let's say we had a spinner on this wheel, and we wanted to find the sample space for the results. The sample space would be a list of all of the colors. So typically a capital S is used to represent sample space, and the values are written inside curly brackets, separated by commas, as we can see here. So now we might wonder, what's an example of a simple event, or what's an example of a compound event? One answer for a simple event might be red. See if you can come up with the others. For a compound event, we may have any collection of simple events. So I have green, teal, blue, indigo, and violet. Let's look at another example. So what would the sample space be for grade levels in a high school? They would be freshman, sophomore, junior, senior. See if you can come up with some examples for simple and compound events for this sample space. Now let's talk about the types of sample spaces that we may see. The first is discrete. In a discrete sample space, the sample space can be listed. It may include categories, and the sample space will be countable. The two examples that we looked at before were both discrete sample spaces, and this example here of the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is also discrete. We can definitely count that sample space. The other type of sample space is continuous, which has a sample space that cannot be listed. Typically, a continuous sample space will contain decimals. An example may be that all the x's such that x is greater than or equal to 5. This is impossible to list out because it will contain infinitely many values. Let's talk about some more vocab. Probability is the relative likelihood that an event will occur. We'll talk about empirical, classical, and subjective approaches to probability. The law of large numbers tells us that as the number of trials in an experiment increases, the average of the outcomes will approach the expected value. Let's also look at some notation and notes. So, to write the probability of an event, we have a P, the capital P, and then inside the parentheses we will have our event. So we're calling our event E in this case. Probability is typically written as a decimal, but you can also think of it as a percentage. The probability of an event is always going to be between 0 and 1. You can include 0 and you can include 1. Consider for a moment what a probability of 0 means and what a probability of 1 would mean. The sum of all probabilities of all the probabilities of simple events in a discrete sample space will equal 1. Now let's talk about the empirical approach to solving probabilities. This approach will involve data found through observations or experiments, and relative frequencies are used. So an example is if we wanted to find the probability of a person having a dog, we may take a survey and then divide the number of people who had a dog out of the total number of people that were surveyed. Next is the classical approach. This is when we'll know the probability a priori by the nature of experiment, and all of the probabilities are assigned before experimenting. So, for example, we can find the probability of obtaining doubles when rolling 2 die without needing to perform an experiment. So let's try it out. So what would the probability of rolling doubles be? The probability would be found by dividing the number of doubles that are possible by the total number of possible outcomes. So there are 6 ways to get doubles and 36 total outcomes. So the probability of rolling doubles would be 6 divided by 36, which we can reduce to 1/6, or we can write this as a decimal, which would round to 0.1667. I typically like to use 4 decimal places when I'm writing out probabilities, but make sure to pay attention to what you're asked to round to. And finally, we had the subjective approach. So this is based on prior experience, and there's no repeatable random experiment that we can use. So one example may be, what's the probability that I will win $1 million next year? How can we solve this? Well, the best ways, or pretty much the only ways that we may be able to solve this or answer this question are by asking experts or using our personal judgment. And that's how we would approach it. So it's definitely less exact than some of the other methods. So now we're going to talk about some more vocab associated with probabilities, the first of which being complements. So the complement of an event is everything that's in the sample space except for that event. So in this image, if the entire image represents our sample space and the white circle is the event, the green will represent the complement of the event. So to write the complement of an event E, we will either write E with an apostrophe or E raised to the C. That's the notation we would use. An important note is that the probability of an event plus the probability of its complement will equal 1. Now let's talk about unions. The union of 2 events is all outcomes of either event or both events. So let's say we surveyed a group of students in a school about whether they had a dog, a cat, or neither. If the entire box here represents all 3 potential answers, which is our sample space, the first circle is the event that a person had a dog, and then the second circle is the event the person had a cat. We can see that the union of the events of having a dog and having a cat is colored red. This red space would include all the people who either have a dog, have a cat, or both, and the white part on the outside will only include people who have neither. So the symbol for union looks like a giant U, which makes it easy to remember. And we can either read the symbol as union or as or. Finally, we've got intersections. The intersection of 2 events is all outcomes in both events. So if we go back to our cat and dog example, the intersection is all of the people who have both a cat and a dog, which is the overlap in this image. The notation, or the symbol for an intersection, is the same as the symbol for the union, except that it's flipped upside down. We can read this symbol as intersects or as and. So they have a cat and dog. Now we're going to look at a law for probability called the general law of addition. So this is the formula for the general law of addition. It's not very easy to read in this form, so let's break it down by parts. So here we go, it's by color. Reading from left to right, this says the probability of the union of two events, there's the left part, is the probability of the first event, which is P of E, plus the probability of the second event, which is the P with the F, minus the probability of the intersection of the two. So let's look at a little example that will help us consider why we have to subtract the probability of the intersection of those two events. When randomly selecting a card from a deck of cards, what's the probability of selecting an ace or a diamond? So remember that the word or is used when we have a union. So this question essentially asks us to find the probability of the union of picking an ace and picking a diamond. I filled in the general law of addition equation, but let's take this one step at a time. So we know that we're going to need to find the probability that we get an ace. So since there's 4 aces in a deck of cards and 52 cards in total, we need to divide these to get the probability of getting an ace. Next thing we're going to need is the probability that we get a diamond. And in a deck of cards, there's 13 diamonds out of every 52 total cards. So if we divide these, we'll get the probability of getting a diamond. The last thing we're going to need is the intersection of getting an ace and a diamond. And there's only one ace of diamonds in a deck of cards, so the probability of getting that card is 1 out of 52. I've put all the probabilities that we've just found under their places in the equation. So if we solve that side, we get that the probability of getting an ace or diamond is 16 out of 52, which is roughly 0.3077 or 30.77%. Take a minute to think about why we had to subtract the probability of getting the ace of diamonds. We're going to touch on this idea again soon. But first we have a few more vocab words to go over. Mutually exclusive or disjoint events are events whose intersection is the empty set, and the empty set is a set with no elements in it. If events E and F are mutually exclusive, they have no intersection, and you can simplify the general law of addition to this, which is the special law of addition. We can read this as the probability of the union of two events is the probability of the first event plus the probability of the second event. With the general law of addition, we needed to subtract the probability of the intersection because otherwise we would be counting it with both the first event and the second, and we didn't want to double count it. But now, since the intersection is the empty set, we know we won't have this problem. So let's talk about a few examples of mutually exclusive events. The first event is at noon on Sunday, I will go to the store. And the second event is at noon on Sunday, I will stay home. If we assume that these two events are for the same Sunday, then they must be mutually exclusive events because I cannot stay home and go to the store at the same time. If we knew the probability of each event, we could find the probability that I will go to the store or stay home by using the special law of addition. Let's also quickly look at conditional probability. Conditional probability is the probability of an event occurring given that another event has already occurred. The notation to the left here is the way we write conditional probability. The vertical line is read as given. We can calculate the conditional probability of event E given event F by dividing the probability of the intersection of the two events by the probability of event F, as long as the probability of event F is not 0. Let's also briefly look at how to calculate odds. So odds in favor of an event are calculated by taking the ratio of the probability that an event will occur to the probability that the event will not occur. So for example, to calculate the odds in favor of event E, we divide the probability of event E by the probability of the complement of E, which is the same as dividing by 1 minus the probability of E. Calculating odds against E is very simple. All we have to do is switch the numerator and the denominator. If we wanted to calculate the odds in favor of winning a game, we would need to divide the probability of winning by the probability of the complement of winning. Try to figure out how we would calculate what the odds against winning would be. The last thing we're going to talk about today are dependent and independent events. And this certainly isn't the last topic included in your text, so be sure to explore that more as well. So we want to know how to tell if events are dependent or independent of one another. And the best way to check if the probability is if the probability of event E given event F is different from the probability of event E. This would tell us, if they're different, that the events are dependent of they are dependent of one another. So if we have independent events, we can tell that events are independent if we know that event F occurring does not affect the probability that event E will occur. And that is all for this video. If you have any questions, head over to the learning community by following the instructions on screen here. Thanks for watching.